Okay, so this video is about solids of revolution, but the problem is that solids of revolution by itself is a topic that I consider boring and useless. Because think about it, what is it really? There is a formula in the booklet, and then they're going to give you an example. You apply the formula showing that you know how to apply formulas, but then again, you've already showed that with so many other formulas before. And then, of course, the exercise becomes more interesting because it sets up an integral for you to solve, and that is a very good skill to have. You're going to show that you know how to solve integrals. But then again, if that's the point, they might as well just give you the integral and ask you to solve it. So what is the solids of revolution for? What actual new knowledge are you getting from that you wouldn't get if that was not part of the syllabus? So that is kind of what I want to talk about. I don't really want to stand here and solve exercises about solids of revolution because that would be boring. Instead, I want to convince you that yes, solids of revolution can be interesting. Talking about them and examining where the formula comes from, why it is that way, and what other kinds of similar formulas we could explore for different situations with the same kinds of ideas. That is actually something that is going to improve your knowledge of integrals, not your mechanical skills of solving integrals. That's a separate story, but your conceptual understanding of what the integrals are actually doing. So to begin this conversation, I like to ask my students a very simple question. What is the circumference of a circle? And then everybody answers 2 pi r because of course it is. And then I ask, why? How do you know that it is that? Well, sometimes this question gets people a little bit confused because it's a formula that they learned when they were children and nobody was asking them to know why, but not for very long because that is a simple question. 2 pi r is the circumference of a circle because it is, because the number pi is defined to be the ratio between the circumference and the diameter. The diameter is twice the radius, so you move that over there and there you go, that's your formula. But that is an interesting beginning to this conversation because then I get to say that this formula for the circumference of a circle, 2 pi r, does not require a demonstration because it is a definition. But then right after that, of course, I ask, well, what is the area of a circle? And everybody knows that it's pi r squared. And then I ask, why? How do you know that pi r squared is the area of a circle? Does that formula require a demonstration? Does it require a proof? Because the other one didn't. And yeah, calculating the area of a circle is something that requires a proof. We learn as children that the formula is pi r squared, and nobody tells us why back then, because this is going to come from integration. Integration is all about areas. So now I will show you 3 different ways to prove that the area of a circle is pi r squared, not because I think you need convincing that it is, but because I want to convince you that it is interesting to have several different ways to prove the same thing. So integration talks about calculating areas by cutting up shapes into small pieces. So here I have 3 circles and I'm going to cut them up in 3 different ways. So there you go. The first one is cut up into vertical stripes, which maybe is the more usual one. Second one is like tiny thin pizza slices, and the third one is concentric circles. And this is not the most important observation here by any means, but if the pizza slices look to you like they are bigger than the shapes in the other pictures, that's an optical illusion because of their shape. If you actually count how many of each color I've used in each of these pictures, the bigger ones are these because I needed fewer of them. It's just that the pizza slice is so much smaller in the middle and it gets bigger as the slice gets closer to the circumference. But anyway, integration works by calculating a bigger area as a sum of smaller, easier to calculate areas. And that is exactly what we are going to do in each of these 3 cases. The first one with the vertical stripes is the usual Riemann sum that you've probably seen before. The radius of the circle is r, so I've put the x's here and I'm integrating from minus r to r, so from here to here. The 2 here is because I'm going to use the top half plus the bottom half, and they have the same length. And the function that I am integrating under is the function square root of r squared minus x squared, which is the equation of a circle. And if you want to talk about equations of circles, I have another video about that. But I actually don't like talking about Riemann sum a lot in the beginning of teaching integral. I feel like the idea of adding the areas of a lot of very thin rectangles, like this is the height of the rectangle and this is somehow the base of the rectangle, that is an interesting idea, but I don't think that in the beginning it really helps for the student to actually acquire the skill of calculating integrals, because it's always the same. It's always base times height, and then the problem is never this. The problem is that depending on what the height is, then calculating the integral will be a difficult thing. And by the way, have you thought about what this one's going to be like? So when I'm beginning to teach integrals, I basically don't focus on that. I tell the students to just think of the dx as part of the notation that is telling you what the variable of integration is. Like in this case, it's x and not r, so r is a constant. But this is the moment when I actually start focusing on it, on what this notation means in terms of the Riemann sum, because this is the base times the height, making an area of a rectangular shaped small piece, in contrast to these other differently shaped small pieces that I am also going to want to be adding infinitely many of. And all of these options are going to require in some place some sort of approximation, because this is not a staircase with a bunch of rectangles. This is a smooth circle. So when we are adding it like this, we are approximating it as a staircase. Here, the approximation is going to be different, because the thing is, each of these colored circles here, well, if you think of them as circles, then they don't have any area, but they are not circles. They are like thin circular bands. And this is how I'm going to calculate their area. Here is a circular band. Now I'm going to cut it up, and now it's a rectangle, and I'm going to do it base times height. The height is very small. That's going to be the dx or d whatever in the picture. But the base of this rectangle is the length of the band, which is the circumference of the circle that it came from. So I've put this axis going kind of diagonally like this, just to represent the fact that it doesn't have to be a horizontal and vertical axis, because that's not what we're doing. We're not doing Riemann sum right now. So that's just a random axis that goes from the center of the circle out. The integration is going to go from 0, which is in the center, all the way to r, which is the radius of the circle. That's the last circular band that we're adding up. Each one of them is just like I was showing you, is 2 pi t. I'm calling the variable of integration here. So it's the circumference of that circle times the tiny little width that it had. So it's a bunch of these in different lengths that are being added together. And I just wanted to call my variable t just so that it isn't x, because, well, for the same reason that I put the x's diagonally here, right? I just want to stress that it's not necessarily in a coordinate plane, but you could call it x if you wanted. But for the third option, for the pizza, I'm not going to put an axis, because the colored things, the little pieces that I'm going to be adding, they are going around a circle. It's not an axis. This is going to rotate. So whatever I call my variable of integration, it's going to go around the circle one full time. So it's going to go from 0 to 2 pi. I think I'm going to call it theta for an angle. And each one of the pizza slices looks like this. There is a tiny little angle there, which is a d theta, which is completely equivalent to the tiny little base of the rectangle here being dx, and the tiny little width of the circles here being dt. This time it's a tiny little angle that is called d theta. And I said that all of these things involve approximations, right? So in the case of the circular bands, well, if you look at one of them, choose one with your eyes and look, the outside circle of the band is not exactly the same as the inside circle. So you can't really unwind them into perfect rectangles, right? Because the inside circle of this thing is a little bit smaller than the outside circle. It has some width. even though it's a small width. This is working because this is elastic, it stretches. So they are approximations, but that's fine. That's how integration works. But in the case of the pizza slices, what they really are circular sectors. I can't, however, calculate the area of a circular sector before I know what the area of a circle is. And that is what I'm trying to figure out in this situation. So I am going to approximate the pizza slice as a triangle. I can do that because it is very small. I know it sounds more surprising when we are talking about the pizza than in the other two examples, but trust me, it is exactly the same kind of approximation that is going on here. So that is a triangle. The area of a triangle is base times height divided by 2. The height of this triangle is the radius of the circle. And for the base of the triangle, I'm going to use the circular arc. That I can use because I already have the circumference, which is 2 pi r. And notice how I'm being very careful not to give you a circular argument. I am only using things that I have already talked about. I can't use the same thing to prove itself, which is why I can't use the area of a circular sector to prove the area of a circle. But anyway, the circular arc is the radius times the angle. So it's going to be r times d theta. Two of these integrals look really easy to solve. The third one does not, but they all should have the same answer, which should be pi r squared. So now let's go ahead and solve all three of them. So I'll start with the easier ones. This is the one with the concentric circles. And this integral has a 2 pi that is a constant. I can just put it outside. And then after that, it's the integral of t dt, which is just t squared over 2. But that's a definite integral from 0 to r. So when I apply it to r and to 0, well, this one is just 0. This 2 cancels with that 2. And our result is pi r squared like we wanted. The pizza one is also quite easy because this is r squared over 2, but r is a constant here. The variable of integration is theta. So you can put the r squared over 2 outside, and then the integral is just of d theta. So that from 0 to 2 pi is 2 pi. The 2's cancel, and the answer is again pi r squared. So far so good, but the third one, the vertical one, is not going to be that easy because this is an integral in dx, and the x is showing up in a configuration that calls for trigonometric substitution. It's something minus x squared inside of another function, which is the square root. So let's use x equals sine of t. Actually, I said it wrong, but I wrote it correctly. It's an easy mistake to make. X equals sine of t is the correct substitution for when you see the minus x squared, but then this is not 1 minus x squared. This is r squared minus x squared. So to compensate for that r squared, you actually need to substitute x equals r times sine of t, because then when this x gets squared up here, this r will also be squared, so you're going to have a common factor of r squared there to get out of the square root. But before we get there, let me just write down dx dt, the derivative of sine is cosine, and now I'm going to start substituting. That too I just put out of the integral to simplify it. Now in the square root we have r squared minus, and then that's exactly what I said was going to happen, r squared times sine squared. And the dx over here also needs to be substituted. This dx is r cosine t times dt. If you multiply both sides of this equation by dt, that's what you get. But the r squared as a common factor in the square root does get out of the square root, like I said, and then it's just r outside times this other r here, and both of them are constants. So this r times r is also going to go out of the integral. And then what's happening here, and this is the kind of thing that always happens in trigonometric substitution, it looks like a happy coincidence, but it's not. It's intentional. That's why in this kind of situation we pick this kind of substitution, is because when we get here, we have 1 minus sine squared which is just cosine squared by the Pythagorean identity. And then the square root of cosine squared is cosine. Well, now you have two of them, cosine times cosine. So that is a cosine squared. And the integral of cosine squared is one of the most annoying ones there is. I could probably do a whole video just about that one. But for today, I'm just going to pretend that I know the answer by heart, or that I looked it up somewhere, or that I did it in a corner of the page, and I'm going to put the answer right here. So not only is the traditional way to cut up the circle, which is vertically with the Riemann sum, turn into an integral that is far more difficult than the other two that we just did before, but it turns into a especially annoying one, which is the integral of cosine squared. And I'm not done yet because there was a substitution in the beginning, so I need to reverse this substitution now. So sine of t is x over r, and then cosine of t, if you use the Pythagorean identity again, is the square root of 1 minus x over r squared. These things sound very complicated when you just say them out loud without looking at them, but it's this squared, 1 minus that, and then square root. And then for t here, you're going to need an inverse trigonometric function, because if sine of t is x over r, then t is the arcsine of x over r. Now, to make things at least a little less complicated, at least there is a 2 out there that cancels with this 2. And now that I've undone my substitution from t back to x, I can rewrite my limits of integration of that definite integral that I haven't been using so far. So it's x going from minus r to r. Let me put that here. And now I just have to plug in the limits of integration. So when I put x equals r here, I get arcsine of r over r, which is 1. And then this term here is going to be 0, because this over this is 1. 1 minus 1 is 0. This term actually turns into 0 when you plug in x equals minus r as well. And the other one over there is arcsine of minus r over r, which is minus 1. And it's a good thing that the numbers that appear are numbers that we know and not just some random numbers, because the angle whose sine is 1 is pi over 2. And the angle whose sine is negative 1 is minus pi over 2. So you get a minus minus here, which is plus. And there's your answer. Pi r squared is the area of the circle. So now we come to volumes of three-dimensional things. Maybe you know that this is the volume of a sphere, and maybe you don't, but it doesn't matter, because the point is that we're going to prove it. And then you're going to know. At this point, the conversation begins to look a little bit closer to solids of revolution, which, remember, is where we're trying to go to, because at least this is a solid, and it is a solid of revolution. Look at it. You take a circle, you rotate it, you make a sphere. But what you should be keeping in mind right now, because of the conversation that we've spent the past few minutes having, is that we want to calculate the big volume of the big sphere by adding up a bunch of small volumes, which is going to be an integral. We're going to be integrating over a bunch of small volumes that we cut the sphere into. Just like we've done with the circle, we've cut it up into a bunch of smaller areas to calculate its whole area. And the most important thing here, this is the point, is that you are allowed to be creative in the shapes of the small volumes that you're going to cut your sphere into. Maybe you've learned integration by believing that integration is Riemann sum. But now you've seen that it doesn't have to be. You can cut up the shape into different shapes. And by the way, the Riemann sum was the worst one. That was the difficult integral. The other two were much easier. So that's what we want to talk about now. What are the smart ways that we can possibly cut up a sphere into a bunch of smaller volumes to integrate over? And there are multiple ways that you can think of to do that. For example, you could take something like this, and I'm going to get really close now so you can see. The camera doesn't really want to focus on it too well, but it is a bunch of tiny, tiny little squares. And you could put this on top of your sphere and just push it down like this. You're going to get like very, very thin square-based prisms. That would be a terrible way to integrate the volume of a sphere, and I'm not going to explore it in this video. But a second idea that you could have is to just slice it horizontally into a bunch of circles. Circles that still have like a very small thickness. They are paper thin, but they are technically cylinders because they have volume. So the volume of each one of these cylinders is the area of a circle times the thickness. And I am not going to attempt to draw that, but please imagine this sphere is sliced horizontally into a bunch of circles. Well, of course, you could have sliced it vertically or diagonally in any direction because a sphere is round, but I said I was going to slice it horizontally, so I'm sticking with my choice. I am going to integrate along this vertical axis here. I'm going to call that variable z because why not? And I'm going to integrate from minus r to r, the area of the circle times dz, which is the thickness of the paper thin circles we were talking about. And I said I wasn't going to draw, but I am going to draw just one circle to show you. So I picked an arbitrary value of z, and at that height, I've drawn the circle that I am talking about. Now I need to figure out its area. And what I need for that is the radius of that orange circle, which I'm calling x in green in the picture. Of course, there's also z in the picture, which is the arbitrary height that I chose to illustrate. And I've put a little right angle there so that you can see where this is going. I'm going to close that right triangle with a hypotenuse whose measure is the radius of the sphere. So now we can get x in terms of r, which is a fixed value, and z, which is our variable of integration. And pi x squared is going to be the area of the orange circle that we want to integrate. And I am aware that that square root cancels with the square, but I wanted to write it this way just to show you that this is basically solids of revolution right there. This is where the formula comes from. You've got the pi times the x squared, and the x is in terms of the variable of integration z. You're not used to seeing it called z. The vertical one would be y, and this is the situation in which I am rotating around y. There's also the other one in which I'm rotating around x, but those are just variations on the same thing. The point is that the sphere is a stack of paper thin circles of different sizes. It doesn't have to be a sphere, but it does have to be a solid that is rotationally symmetric. So that is the kind of thing that you get when you make a solid of revolution. It's the kind of solid that can be calculated as a stack of paper thin circles. The area of a circle is pi r squared, so that is why the formula goes like this, and this one is the thickness of the circle in the integration. So this one looks kind of scary, kind of like this one that also had that square root and it turned out to be a trigonometric substitution. This one is not actually. This one's an easy integral to solve because the square cancels out with the square root, so let's go do that. So as I was saying, this integral is also not going to cause us any trouble because the square root cancels out with the square. The pi is a constant that can go outside. And now we just integrate this very easy polynomial. The only thing that could possibly go wrong here is if you mess up who is a constant and who is the variable of integration. Because r is a constant here. The variable of integration is z. So when you integrate r squared, the answer is not r cubed over 3. It is r squared times z. Because you can think of the r squared as a number, like 3. So the integral of 3 dz is 3z. That's exactly what's happening here. But the other term, on the other hand, z squared, that is the variable of integration, so the answer is going to be z cubed over 3. And then you start putting the limits of integration into that. Let's begin by plugging in r for z, and then be very careful not to mess up the signs here because there is a minus from the fundamental theorem of calculus, and there's going to be the minus from the minus r as well. So that one is going to become minus r cubed. And this one's going to have a whole lot of negative signs because there's minus in the z, minus, minus, minus because it's cubed, and then minus again. So that's 4 minuses. It's an even number, so that's a plus. When you put all of that together, this is 2/3 of r cubed. This is minus 2/3 because all the signs are reversed. So it's 2/3 minus minus 2/3 of r cubed. So here is your 4/3 r cubed that you wanted. So now I'm going to suggest a third way that you can cut the volume of this sphere. Remember, the first one was the very bad suggestion of doing this. The second one was the thin circles that we were just talking about. And now for the third way, I want you to imagine a cylinder that is going to cut through the middle of the sphere like this. And then you can do that with cylinders of many different radius. So like there's this thin one, which becomes a little bit taller, this slightly larger one that is shorter. And when you put all of that together, they supposedly make the sphere, right? I didn't cut it up intentionally in correct sizes or anything. But I want you to visualize the sphere being cut up from the center vertical axis going outside. And at each point, there is a cylinder that goes all the way through the sphere vertically from whatever point it touches on the sphere here to down here. The first few cylinders in the middle are going to be tall and thin, and then as it goes out, they become short and wider. A paper-thin cylinder is an excellent shape to calculate the volume of because it unwraps into a rectangle, which is just base times height times the thickness of the paper, which is not very big, but it's going to be the variable of integration. I'm going to call it dx here. So x is going to go from 0 to r because it's not just going to the side, okay? It's going from inside out. So it doesn't have to go from negative r to r. It's just from 0 to r. So when you get that radius, then the cylinder is wrapping around both sides and all sides. And now, just like I did with the other example where I picked an arbitrary value of z and drew the circle there, I am now going to pick an arbitrary value of x and draw the cylinder there. Here it is. Now that cylinder is going to be unwrapped into a rectangle to calculate base times height. But in order to do that, I need to figure out the dimensions of that cylinder, and that is going to happen in a very similar way to what happened in the other method that I was doing with the triangle here. So there you go. R is the radius of the sphere. I put height over 2 here because I mean height of the cylinder, okay? So it's half here and the other half is down here. So let's build this integral here. X is going to go from 0 to r. Then I need the base of the cylinder, which is going to be this circumference here, is 2 pi x. Height of this cylinder is twice of the thing that we get by Pythagoras here in the green triangle, and then dx as the thickness of the paper cylinder. And again, of course, this square root of r squared minus x squared keeps appearing over and over because that comes from the equation of a circle. But this is also not a difficult integral. This is not trigonometric substitution because you have the x out here. So you're just going to do a normal substitution. So for this one, first of all, let's get the constants out of the integral. I have 2 pi times 2, so that's 4 pi. And even though there is a square root of r squared minus x squared, which has happened before in this video, and I said that it called for the trigonometric substitution r sine t, let's not get carried away here, because in this case, this is not the good idea due to the fact that there is also an x outside. So there's an easier way to go about this one, which is just the regular substitution where you have a composite function, the square root of something. You take the something and call it u. This is going to work fine in this case because when you do du dx here, the derivative is already outside here. So they're going to cancel. Look, I've put the u for r squared minus x squared, and then the dx is going to come from this equation here. It's going to be du over negative 2x. The x's cancel out like we wanted. This 2 can cancel out with a bit of that 4. And then I'm just going to put the negative sign outside to get rid of the fraction. So in order to complete this integral, I need to write the square root of u as u to the power of half, because then you can integrate it using the power rule. Now let's organize this 3 halves over here, and then substitute back the u as r squared minus x squared. Now that we've done that, you can put the limits of integration here, x going from 0 to r. And actually, I shouldn't have had the limits here, right? Because this integral was written as du. U was not the thing that was going from 0 to r, that was x. But when I substitute r for x here, then this is going to be 0. So I'm only going to have the second part of the fundamental theorem of calculus when I'm plugging in 0 for x. But that part comes with a minus. So that minus is going to become a plus, and this is a 0. Of course, now this is just r squared to the power of 3 halves, and the square cancels with the half. This is r to the power of 3, which is exactly what we wanted. So if you are an IB student, specifically in Math AA high level, and you're just here reviewing your content, you probably have recognized this, but not this, right? So I wanted to show you both anyway. First of all, because not everybody is an IB student, but I also do want to mention that both of these methods are fairly common in calculus courses. They are taught side by side, just like I just did. And the fact that one of them is in the syllabus of the IB and the other one isn't, this feels a little bit weird to me. It makes me imagine people in a room discussing whether or not solids of revolution should be in the syllabus. And then some people were saying yes and others were saying no. And then they reached a compromise by including one and not the other. This is what I'm imagining. But I just feel that this compromise is a really bad solution because, like I said, solids of revolution as it is feels like a pointless topic. You're just taking one formula and applying it and then solving an integral. The beauty of solids of revolution is in the comparison, is in showing you that there are multiple different ways to cut up shapes to do integrals. And if you're only doing ever one of them, then that is lost. So that's why we're here talking about it, isn't it? And now I want to propose the fourth way to cut up the volume of a sphere. This one is not going to turn into a method for calculating volumes of different solids because it really only works for spheres specifically. But imagine a sphere being made up of various hollow spheres, one inside of the other, like you're blowing up a party balloon. So now the volume of that sphere, which we already know is 4/3 of pi r cubed, needs to be equal to the integral from 0 to r, so from the center of the sphere to the outside, of the volumes of all of those concentric spheres. Although, of course, you're not going to use the volume of a sphere to calculate the volume of a sphere. That is circular reasoning, like we've already mentioned before in the circles. But you can say that you are integrating the surface areas of the concentric spheres. So the volume would be the surface area times a tiny little thickness, which is your variable of integration that is going from 0 to r. So let me call that t. But wait, I don't know the surface area of a sphere of radius t, do I? That's why I'm calling S of t here. And yes, I know that you know the formula. I know it too, but we're pretending that we don't know because we are trying to prove these formulas. But here's the thing, I already know the answer, right? Because I've calculated the volume of a sphere in one of those two other ways that I just showed you. So instead, I'm going to do it backwards. I'm going to use the volume to find the surface area. I'm going to keep it as just S of t here. I'm going to use the fundamental theorem of calculus because I know that this is true, right? So if this is the integral of that, then this needs to be the derivative of this. So there you go. The surface area of a sphere is 4 pi r squared. And if you're like me and you have difficulty remembering the formulas, like I have these two memorized, but I have trouble remembering which is which. Which one has the 4/3 and the other one doesn't. So this is the way that I remember it when I need it in my life without the formula booklets. because I know that these are the formulas, and I also know that the surface area needs to be the derivative of the volume. So then I put the things together in my mind and I come up with these. Another topic that very traditionally is part of calculus courses and that has nothing to do with volumes, but also explores this idea of integrating not just the boring old rectangles, but different types of small amounts being added, is this thing where you want to calculate the length of a curve. Calculating lengths of things that are straight is very easy, and calculating the length of something that is curved exactly like a circle, we also have formulas for, but I'm talking about an arbitrary shape like a function, and you want to calculate the length, say from 0 to k, the length of this curve. And you're going to integrate dx with x going from 0 to k, but clearly that's not the only thing that determines the length of the curve, because the blue one is also going from 0 to k, and it's clearly much longer, right? Because it came up more, it came down more. So how do you calculate these things? Well, it's the same kind of idea. You're going to add up a bunch of small lengths, and as an approximation, you're going to look at all of these small lengths being straight, as if you were doing like many short line segments following this path, approximating the curved shape of the function. And then I'm going to draw just one, but I'm going to draw it much larger than it should be to exaggerate, to show you how to calculate. So look how big I've made that dx. The point is that the thing that you're adding is not dx. You're adding this. It's the hypotenuse of the triangle, yes. So again, we're going to have to use Pythagoras in some way there, but so far the only thing that we know from that triangle is the dx. Well, we also know at this point, we know the function, so we know the derivative of the function, and the derivative is the slope of the tangent line, so it's rise over run. So f prime is this vertical over dx, which means that the vertical length there is f prime times dx, and then we're going to use Pythagoras for that hypotenuse. I didn't want to write down dx squared, so I just did it with the dx outside of the square root, which is also more convenient for when I'm going to write my integral now, because remember, that triangle is not supposed to be huge like that. It's supposed to be a tiny, tiny little triangle. So it's good that the length of the hypotenuse is something times dx, because it makes it very, very small. And then I can integrate over all of these many small segments. So that's how that formula goes. And I am pretty sure they have explored this in a paper 3 question at one point. And paper 3 questions are really cool like that. They get to explore things that are very, very close to the syllabus, but not quite part of the syllabus. So they lead you through exploring new things that you are able to do because you've almost studied that. You got really close within the syllabus. But on the other hand, under pressure during an exam, it's very tempting to just like, because they gave you the formula. So it was totally possible to go through that paper 3 question not understanding any of these things, just applying the formula that they gave to you and then calculating some integrals. So I find this topic fascinating. I know that I started the video saying that it was boring, but by now you've understood that I meant that what's boring is the fact that only a tiny little bit of all of this is in the syllabus. We can also try to explore the surface area in a different way, because I've done everything in multiple ways, and the surface area I just did as the derivative of the volume. So I'm going to use this as an example of how, even though this is all beautiful and fascinating, the fact that we can cut up our shapes in creative ways, we do still need to be careful, because it is possible to get this kind of thing wrong, okay? So let me show you something that you might think look exactly the same as all the other examples that we've been doing, but it's going to go wrong. And then I'm going to explain to you where it went wrong and how to fix it. So the thing is, I want to think of the surface area of this sphere. The sphere is hollow, right? So if I cut it horizontally in a bunch of circles, it's not a bunch of circles, it's just a bunch of circumferences. And never mind, the stuff that is drawn on top of the sphere has nothing to do with what we're talking about today. This is just something that I used it for another video and I never erased it. But here's the thing. Circumferences don't have area, they have length. So if I want to add a bunch of circumferences to make up my whole hollow sphere, I need to think of these circumferences as having a little bit of width so that it becomes an area instead of a length, something like this. Of course, this is exaggerated, it is way too thick, but you imagine it being small, 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 as a dx or a dz in this case. So then you have another circle farther up here, and so on and so forth. So that's exactly what I'm trying to draw here. There's this sphere with an arbitrary height highlighted in orange, and that thing is supposed to be the tape measure going around the sphere. Let's do a right triangle like we did the other times. You have the z, the x, the r, and then you're going to integrate from the bottom of the sphere to the top of the sphere, so from here to here, and then it is the circumference, 2 pi x, times the width of the tape measure, which is dz, our variable of integration. But the problem is that it doesn't work. And you can follow my calculations here if you want, and I'm sorry I didn't want to go through the same trigonometric substitution again, but you get pi squared r squared in the end, and that's not what you wanted. You wanted 4 pi r squared. And the problem is that we are placing our pieces wrong. Over here in the equator of the sphere, everything looks fine because the tape measure is right on the surface. But when you get up here in the very tiny ones, this tape is nowhere near the surface of the sphere. That's not actually the correct shape to cut it into. You can still cut it up into small areas, but the areas can't be vertical like this. Like the DZ in this picture was vertical, and you see I've drawn it vertical as well, sticking out of the sphere, just like what was happening in real life, but that is not the correct shape to add. You want to add areas that are on the sphere. So the correct way to do it would be much more like this blue one here, where the tape is not sticking out of the surface, but it is laying down on the surface. And of course, the top circle and the bottom circle in the blue tape here are not exactly the same, because the top one is always going to be slightly smaller than the bottom one. But that is the kind of approximation that doesn't matter. Now, using something vertically when it should be diagonal is the sort of approximation that does matter. So in that wrong calculation that we were doing, we were using this vertical orange dz as the width of our tape measure, but that is not correct. We should be using the diagonal one here on the surface of the sphere. Now, I didn't even want to name that because it is not an axis. So instead I named the horizontal one as dx because that makes sense. And then I'm going to try to calculate the diagonal one, which I actually have to use as the width of that band. And the thing is that x squared plus z squared is r squared because this is the equation of a circle. I know that it's a sphere and not a circle, but I am not looking at y right now, just x and z. So if you want, you can think that this is a cross section of the sphere through the plane y equals 0. And then the cross section of a sphere is a circle, which is that circle, so we're fine. That is the relationship between x and z. R is a constant, which is the radius, but notice that that is not exactly what I want. I don't want the relationship between x and z, but between dx and dz. So in other words, not the coordinates of the point of the circle, but how they change as we walk along the circle. How they change is dx and dz. That is the relationship that I want, so that I can calculate the hypotenuse of my tiny triangle there. So there's multiple ways that you can get from this relationship to the one that you want, but I am going to do it with implicit differentiation because I think that's going to be fastest. And I am going to differentiate both sides with respect to x. So the first thing that you should notice is that the right side is going to be 0 because r squared is just a constant and the derivative of a constant is 0. And then on the left, we have the x squared term, and the derivative of that is obviously 2x. But, and this is how implicit differentiation works, when you go to z, you have to be careful because z is not a constant. R was a constant, so the derivative was 0, but z is not a constant. Z depends on x, so we do have to use the chain rule there. First, we do the 2z, which is the derivative of the outside of the chain, and then the inside of the chain is how z depends on x. So that's dz dx. And if you don't really feel comfortable with implicit differentiation yet, then I strongly recommend that you isolate z in terms of x in the first equation. Just take the derivative, simplify, and convince yourself that this is the same thing. And now I can just divide both sides of the equation by 2 and manipulate things a little bit. And it turns out that this is the relationship that I want. Now I can do Pythagoras to find that hypotenuse over there. I know it looks strange with the dx squared and the dz squared. We don't usually square these things, but that's okay because we're doing it inside of a square root. They're going to come outside. So now I've just substituted this into the dx, and now I am going to factor out this dz squared and take it outside of the square root as just dz. This looks a lot more normal, and now I can just simplify this fraction as well. It just turns out that it's going to simplify the calculations if I put them both in the same denominator now. But the thing is that there is an even more convenient way to rewrite this, because this x is strange to what we're trying to do. Z is not strange because it's going to be our variable of integration because we want it to be there. And R is not strange because it is a constant that has a meaning in our situation, which is the radius of the sphere. X is just an auxiliary variable that we put in the picture to calculate this. So we would prefer to have an expression here that doesn't depend on x. So lucky for us, z squared plus x squared is just r squared, so I can substitute that. And then because I really want to get rid of the x, I can write x squared as r squared minus z squared. So there, this is the width of the blue band that is circling our sphere at various heights, depending on z, of course. And that is the width that we should calculate the area of this bandwidth. So it's going to be 2 pi r times this. I'm sorry when I said 2 pi r just there. I hope you understood that I meant the radius of the blue circle, right? That r is not the radius of the sphere. So 2 pi, the radius of the circle is this, which is basically for the same reasons as something we've done over and over in this video. And now I'm going to multiply that by the width, which I've just calculated, making it into the thin rectangle that wraps around the sphere. But look, how convenient! This cancels with this. The denominator of this fraction is the square root of r squared minus z squared, which is exactly the same thing as we're multiplying by. And now the square root cancels with the square. 2 pi r is constant because the variable of integration is not r, it's z. And z going from minus r to r is just 2r, which gives us 4 pi r squared for the surface area of the sphere like we wanted. So now we've calculated with a second method. Remember, the first method was as the derivative of the volume, which is also very cool. Much easier than this, but I insisted on showing you that this also works because all correct paths must be correct. So if you've liked this video, there is another one in which I have calculated the volume of not a whole sphere, but a weirdly cut piece of the sphere. But in that video, I only did the volume. I did not calculate the area of the weird piece of orange. So if you want to do that now with some of the techniques that we've just discussed, I think you can also calculate the surface area of that shape. So let me know.